Recall that the Archimedean property states that for all values of a and b in the real numbers, if a is positive, then there will always exist at least one natural number n satisfying the inequality b is less than a times n. Now, the Archimedean property itself is fairly difficult to prove, and it involves using the completeness axiom. But despite that, it's a remarkably easy property to use. You'll notice that the conclusion of the Archimedean property tells us the existence of a natural number that satisfies a certain inequality. This means if we're ever trying to prove the existence of a natural number satisfying a certain inequality, the Archimedean property can be a useful tool to use. All we need to do when we're trying to prove the existence of a natural number satisfying a certain inequality is decide what values of a and b we want to use in order to get the inequality that we're looking for. To see how this works, let's look at a few simple examples. In our first example, we're going to show that for any value of x in the real numbers, we can always find a larger natural number. In other words, we can always find a natural number that is strictly greater than x. To prove this, since it's a statement about all real numbers x, we of course need to start by letting x be an arbitrary real number. At this point, we're required to demonstrate the existence of a natural number that satisfies a certain inequality, which means this might be a good job for the Archimedean property. Let's get out a scrap piece of paper. The Archimedean property tells us that for any values of a and b we choose to talk about, if our value of a is positive, then we're guaranteed the existence of a natural number satisfying the inequality b is less than an. The question is now, how can we use this to get the inequality we're looking for? We want to show that there's a natural number satisfying the inequality x is less than n. Comparing our inequality to the one that we can get from the Archimedean property, we can notice that a good choice of the value of b would be the number x, and a good choice of the value of a would be the number 1. And we can notice that the number 1 is a perfectly valid choice for a because the number 1 is positive. Let's return to our proof. Using the Archimedean property, we can say since x and 1 are real numbers, with 1 greater than 0, the Archimedean property says there is at least one value of n in the natural numbers, for which x is less than n times 1. For this value of n, we then have the inequality x is less than n, which proves there is at least one natural number n for which x is less than n. And of course, since x was arbitrary, we can conclude that this is true for all values of x. Let's look at another example. In this example, we're going to prove for all values of x in the real numbers, if x is greater than 0, then there will always be a natural number n for which 1 over n is smaller than x. In other words, whatever x is, no matter how close to the number 0 x gets, there will always be some natural number where 1 over n is even smaller than that. Let's try to prove this. Of course, since we're proving this is true for all values of x in the real numbers, we begin by letting x be an arbitrary real number. Next, we'll notice that this is a conditional statement, and if we're using a direct proof, we would assume that x is greater than 0, and we would then be required to demonstrate the consequent that there is at least one natural number n for which 1 over n is less than x. At this point, we can notice that the statement we're trying to demonstrate is a statement about the existence of a natural number n that satisfies a certain inequality. Again, this suggests to us that we might want to use the Archimedean property. Let's again get out a scrap piece of paper. Recalling that the Archimedean property tells us for any values of a and b in the real numbers, if the value of a we're talking about is greater than 0, then we're guaranteed the existence of a natural number satisfying the inequality b is less than an. The question for us is that given our arbitrary value of x, which we've assumed to be greater than 0, how can we show the existence of a natural number n satisfying the inequality 1 over n is less than x? The trouble with our inequality is that it doesn't look very much like the inequality we can get from the Archimedean property. However, with a little bit of manipulation, we can make them look a little bit similar. If we take the inequality we're trying to get, 1 over n is less than x, and multiply on both sides by n, we get the inequality 1 is less than nx. And this is now starting to look a little more like the type of inequality we can get from the Archimedean property. All we have to do is choose to talk about the value of b being 1 and the value of a being x. And again, since we know that x is positive, x is a perfectly good value of a to talk about. Let's return to our proof. We can say since 1 and x are real numbers, and x is positive, the Archimedean property tells us there is at least one natural number n for which 1 is less than n times x. Now we need to do a little bit of manipulation to this, so we should probably introduce n as a constant into our proof. Remember, from the principle of existential instantiation, if we have a statement in our proof that is known, and that statement includes an existential quantifier, what we can say is that this natural number n exists, but we don't know what value it has. And so all we can do is introduce n as an unknown constant into our proof. We can include a line that says let n be a natural number, satisfying the inequality 1 is less than x times n. The Archimedean property tells us that such an n exists, but it doesn't tell us what it is, and so this value of n has to remain unknown. However, with this value of n, we now have the inequality 1 is less than x times n, which we can manipulate to derive the inequality that we're trying to get. We can simply say since all natural numbers are positive, n is positive, and so is its inverse, and so we can multiply the inverse of n on both sides of our inequality. This gives us 1 over n on the left-hand side and simply x on the right-hand side. We've now demonstrated that there is at least one value of n, the one that we get from the Archimedean property, that satisfies the inequality 1 over n is less than x. And of course, our conclusions follow.